So homework 0 is out. If you haven't seen it, it's on the course website. It's a PDF. If you're having trouble accessing it, email me or post on Piazza. I can put the links in many different places. Also, reminder, I did start student hours. The first homework, you probably don't need student hours, but I do get a little bit lonesome because it was just me on the Zoom call by myself for a while. I think I had 2 students drop by, say hello, then they left. Thank you to those students, you know who you are out there. If you guys have like, 5 minutes to just say hi to me, I think that would be great. Otherwise, I'm kind of just, it's just me preparing lectures. So just me and some algorithms. Cool. Yeah, like I said, maybe just say hi. Also, I'm new to Greensboro. So if you want to just come in, drop by and say like, hey, I think this weekend there's this really cool thing going on that you should come check out. That's also cool. Also, this will prevent me from making it part of your first homework to come visit me in student hours. Like, don't force me to do that. If a good chunk of you join my student hours just to say hello and I get to know you, that will prevent me from adding this for the homework assignment. All right. If the student hours don't work for you, on the course website under staff, there is a link to schedule an appointment. Feel free to schedule a 15-minute appointment. Normally, my entire calendar is open. I will try to be like adjustable to your schedule. So if for some reason student hours are not working for you, schedule this just to come, like this would be just to come say hello. Yeah. All right, let's get started. Any questions on those announcements? Cool. All right, so today we're going to be covering Karatsuba's algorithm, and we're going to be doing some pseudocode practice. So here are the big questions. As you guys remember, this class is all about answering how fast is fast enough. Okay. We are also going to be covering how to conquer through division. So divide and conquer. You guys probably are familiar with that technique. How do we handle failure? How do we keep going in the face of uncertainty? And then we're going to practice with pseudocode. So this is the general outline. You guys keep me honest to this for the lecture. But first of all, we're going to recall where we ended last lecture. So I think I was asking you guys, how fast is integer multiplication, right? We have these 2 big integers of size n. And the question we're asking is how many 1-digit operations is it going to take? Did you guys get a chance to think about that when you went home, maybe? Anybody have an answer? Yep. You got. Yeah. Sure, go ahead. Oh, yes. C. Dustin from Zoom agrees with you. He got n squared. Okay. Yeah. You also recommended like the addition operation? Yep. There were also addition operations. Yeah. So I think this is probably what n squared multiplies, 1-digit multiplications. Yes. And then the s is a number of additions, or the number of shifts that you have to do. That's a good point. All right. Yeah. This is actually. Sure. So the great thing about big O notation is that all the extra stuff doesn't matter. If you'll notice, this n squared is the dominating term. These are linear terms. So really, we're just going to focus on the n squared part. So for all intents and purposes, your grade school multiplication algorithm takes n squared operations. The easiest way to see that is that for each element here, you can imagine it's like a nested for loop. One element you have to multiply with all n elements, right? So that's n operations. And you have to do that for each single element in your bottom value. So you have n squared, right? N times n. How many times do I do n operations? I do them n times. So that's kind of like the hand wavy argument. More concretely, there's like additions, there's shifts, there's like sums you have to do, but we're not going to worry about those. Great. Yeah, like I said, technically n squared operations, at most n squared additions. Technically, we're going to forget about that part. So in general, we will say that for normal multiplication, so grade school multiplication runs in time big O of n squared. Cool. We will do the formal definition next lecture. You guys don't have to worry about that right now, but just keep that in mind. So the question that I left everyone in class with is, if we do normal grade school multiplication in n squared, can we do it faster? All right, so that's actually what we're going to be covering this lecture. What do you guys think? Do you think we can do multiplication faster than the normal grade school multiplication that everyone is taught, that third graders can do? Yes, maybe. You guys think you're college students, so you should be able to come up with something better, right? You know, if a third grader can do it, we can do better. Is that right? All right. So I do want to give you guys a reminder in general for big O, and this is not even big O, this is just functions, okay? There is like a hierarchy of how fast functions grow. N squared is basically in this area here, which in general is pretty bad. If you have an algorithm that's n squared in the real world, that's probably too slow, okay? Obviously, there's even slower algorithms that we're going to get to towards the end of the course. Those are terrible. You never want those. And then if you're getting into this area of n log n, of linear, or of constant time, or just log n, these are pretty good. That's what we want. If you have an algorithm that's that fast with your input size, that's pretty good. Because if you think about it, for example, log n grows really slowly. Like log n of, I think, 1,000,000 is like less than 100 or something like that. So even if your problem size is 1,000,000 long, you're only doing like 100 steps. So it grows really slowly. So if you can get an algorithm that is like log n, anybody know any examples already of algorithms that are log n? Yeah, somebody said binary search. So we are going to cover that at some point, but you guys should remember from your previous lecture, or if you've learned it before, binary search is log n. So it's actually very fast. Cool. So let's dig in to see if we can do better. And the technique we're going to cover in today's lecture is known as divide and conquer. So this is a pretty general technique. Usually when you're trying to make an algorithm faster, one thing you can try is take your big problem of size n, break it up into 2 smaller pieces or more, maybe more smaller pieces that are a similar problem, and then keep breaking that down into smaller problems. And then eventually you like bring them together. So somebody mentioned that you guys were pretty familiar with merge sort already. Some of you remember that algorithm. So that algorithm also follows this exact same technique. So today we're going to learn how to apply this technique to integer multiplication. So it's going to feel very similar to merge sort, if you guys remember how that kind of works. But it's going to solve a different problem. And that's the whole point of this class, is for you guys to learn these techniques that you can apply to many different problems. So if you ever have a problem that is n squared or too slow, one thing you can just think in your head is like, I wonder if I can use divide and conquer to maybe make this faster, right? That's where the creativity comes in. You don't know, but you want to try it. So again, if we want to do this for multiplication, looking at this slide, how are we splitting up? So this is our original problem of size 4. And what divide and conquer tells us is we need to figure out a way to split it into 2 smaller problems of a smaller size. So what are we doing here? How are we splitting up this integer? Yeah, we're basically taking these 2 digits, right? We can say that 1,234 is the same as 12, which is a 2-digit problem. Let's say a 2-digit integer, so it's smaller, times 100. You can actually do times 100 very easily, like for free, essentially on a computer. Same way you would do it in your head, because you're like, oh, let me just shift, the number over by 2. Like, let me add some zeros, right? So this is kind of free for us. And then we have another 2-digit problem here, just 34. So using this technique, let's say we're trying to do multiplication now, right? So here's an example from before where we're trying to multiply these 2-digit numbers. How would we use this idea of breaking up the numbers into smaller pieces to multiply them? So we're just thinking of a different way to multiply. Anybody want to take a stab before I reveal the answer? That's close, good idea. Yeah. Perfect. Okay, if you're in this class and you heard these two, I'm forgetting your guys', I think is it Sean? No, it's not Sean. Sorry, what's your name? Yeah, Jonathan and Desmond. All right, if you're in class, Jonathan and Desmond, you guys should become friends with them so that they can help you out in your homeworks, okay? Because they got this. Good job. All right, so that's I think as Jonathan mentioned, we first break up this number into two pieces. So we can do 12 times 100 plus 34. We can break up this number into two pieces, 56 times 100 plus 78. And then you guys can go back to like whatever 7th grade, 8th grade math, and you can like FOIL it out, right? You like multiply this times this. So that's this part, that's step one. Let me actually go through it. So this is one 2-digit multiplication. This is another 2-digit multiplication. This is another 2-digit multiplication. And there's another one over there, I promise. Another 2-digit multiplication. So you can imagine what we've done is we've taken 4-digit multiplication, two 4-digit numbers, and now we've broken it up. So one 4-digit multiplication has now broken up into 4. So now we have more of them to do, but they're smaller, right? That's the whole point. 4 2-digit multiplications. Oh, this is cool. I didn't know I can annotate the slides directly. I'll try that next time. Right. So that's basically here. And you guys figured it out. Does that make sense to everyone? Do you see what we're doing here? So we're just breaking it up into smaller pieces. In general, so don't get scared. This is exactly what you just did, but now I'm throwing in a bunch of variables in there. Not a big deal. It's exactly what you did. If we have, so each of these x's represents 1 digit, okay? So we have an n-digit number, and we're trying to multiply with another. We're having n-digit number, and we're trying to break it up into two pieces, each of half the size, right? In general, if you're trying to multiply two of these numbers together, you will have 4 multiplications, right? So the first thing we do is we take the numbers and we break it up into the first half of the digits. We're going to call this, we're going to call this, I forget what we're going to call this. Then you break it up into the second half of the digits. So for x, this is going to be a, this is going to be b, let's say. Then we're going to do the same thing for y. So we're going to call that c and d. So if we go back to this, this is a, this is b, this is c, this is d, right? So we're going from this example to the general case. So now we're thinking like any n-digit number. So that's why we're introducing all these variables here. But you can see that you can actually follow the exact same steps. So it boils down to one smaller to 4 multiplications, each of which involve smaller digits, because this a and c and b and d are half the size. All right. If you don't get the yeah. So yeah, it would be helpful, I guess, if you guys printed out the slides, you can jot down stuff. But hopefully this makes sense to you. So it's the exact same thing we just did, but I'm using variables. Okay, that's it. All right. So in general, we can actually take one n-digit multiply and break it up into 4 n/2 digit multiplies. And that is what divide and conquer wants us to do, right? We take a big problem of size n, and we break it up into maybe 2, maybe 3, maybe 4, maybe 10 smaller problems, right? So that's the whole point here, right? So what is our pseudocode? So we actually just walked through it, but now we're going to summarize in detail. What does this algorithm look like in pseudocode? So what is the step-by-step that you want to do? All right, so first we start with two numbers, x and y. Let me erase this stuff. Right. And then we're going to do this. If the size of the numbers are 1, so if they're single digits, I'm just going to multiply them directly. I'm just going to tell you the answer. So if I see a 5 and an 8, I'm just going to say that's 40, right? That's what my algorithm is going to return. This is pseudocode, so this is not actually C++. I will share some C++ code that does exactly this, but this is just pseudocode because the first step in solving an algorithm is like, how would you actually step by step write it down, right? Then I'm going to take my x, whatever that number is, and I'm going to break it up into 2 parts, A and B, right? So essentially, you can imagine, how do you do this in code can get a little tricky. But the first thing is you need to understand how the algorithm actually works. So in general, you would take whatever number you have, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, let's go just to 8. And you would say, let me split it down the middle. This becomes my first half. This becomes my second half. So for x, we're going to do that. So my A is 1, 2, 3, 4. My B is 5, 6, 7, 8. OK? We do that for y as well, because we're multiplying 2 numbers. So each number gets split. The x gets split, the y gets split. So now we have 4 pieces, right? And now we just multiply these 4 pieces, because we figured out that to get the answer, we can actually do A times C, A times D plus B times D. This is a typo. So if somebody had caught this before lecture, I'll fix that. If somebody had caught that, this one is a typo. This should be. So AC, AD, which one am I missing? BD, BC. I think this should be BC. So that's a typo. I'll fix it up. If you had caught it, you would have gotten bonus points if somebody had seen the lecture slides before. But once you do these 4 multiplies, which are smaller, right? So the key thing is that A and C are smaller numbers. You can combine them together to get your original answer. So the combination is this part. And again, don't get scared. This is exactly what you did here. This is the combination, right? All we're doing is we're putting letters to the numbers. All right. So that's the algorithm. Actually, there's a lot of details we don't cover here. So like, how do you actually split the numbers? How do you do the shifting so that it's constant time? Because you don't want the shifting to take a lot of time, because then it kind of messes up your algorithm, right? So there are a lot of details that are not covered this, but I will try to share some full code later. So the question now that we want to ask is, after doing all this complicated stuff, is it actually better? So now, instead of giving you your grade school algorithm where you just do like number times number times number, and then you add them up, which honestly is pretty complicated if you kind of think about it, right? But we have 3rd graders do it. So like, this seems complicated to you, but it's only because I didn't teach it to you in 3rd grade. If I went to a 3rd grader and I taught them this algorithm, I think they could do it too, right? So it seems complicated. Yeah, go ahead. Is that? Oh, really? So now we're teaching them how to do carrots. Okay, so maybe in the future, what we'll have to do is we'll be like, everybody remember how to do Karatsuba, and then we'll teach you the other algorithm. And then people will be like, oh, that's so complicated. The normal grade school that you guys learned. All right. But so as you guys remember, so in lecture for algorithm design, what we do is the first step is we're trying to make sure it's correct. We are not going to formally prove that in this lecture. We will get into more of that later. For now, assume the algorithm I told you is correct. Hopefully you guys it makes sense to you because you kind of derived it as we walked through it. So the next question we want to ask is like, does it actually help? Like, is it better? Is this faster? So how do we answer this question? How would we know if it's better? Yeah, back there. Yeah, can you speak up a little bit? That's a great idea. You could try to compare the speed of the, oh, actually I have the think pair share. So yeah, so I guess this is an easier problem than what I'm asking more generally. but if we think about this problem, so we know that if these are 4 digits, we know if we do it the normal way, it's going to take around 16 multiplications, right? It's going to be 4 squared. That's what we said. You guys thought about it last lecture. Somebody said the normal multiplication takes n squared, right? So now the question is, if I do it this new way, if I recurse, how many 1-digit multiplications do you think I'm going to have? So why don't you guys take maybe 30 seconds or a minute to kind of, or maybe let's say 30 seconds to think about it. Maybe ask your neighbor. Yeah, so feel free to ignore the additions. I just care about the 1-digit multiplications at the end. Yeah, what's up? Hey, can you speak up? Includes what? No. Actually, I'm actually just asking like the simplest at the very bottom of the recursion. I'm going to be doing a bunch of 1-digit multiplications. Let's just count those. I don't even care the ones in between or whatever. I don't even care about the additions. I don't care about the combination. I'm just saying like at the very bottom, when I get to just single multiplications, how many of those do you think it's going to take? Also, if you guys want to cheat, the slides are on the course website, so the answer is there, but you know. And also, I'm not asking you to do it for n-digit numbers. I'm actually asking for this specific case. Yeah, go ahead. All right, so somebody says still 16. And here's why. Here's the recursion tree. So we start with 4 digits. We break it up into 4 pieces, each one, which is 2 digits. And then we repeat, right? We take each of these 2 digits and we break it up into 4 pieces. Each of us is 1 digit, right? And now these 1 digits, those you multiply directly. If you remember from the pseudocode, it's like, oh, if the length of my number is 1, just multiply it and then give me the answer, right? So ignoring everything else, right? Like putting that together, you know, the if statements, ignoring all of that, you have 16 multiplications you have to do. So sadly, this complicated algorithm seems, at least for this example, seems to not be better, right? Still 16 multiplications. So what do you think in general? Do you think in general this algorithm is better than your old multiplication algorithm because we're using this fancy technique of divide and conquer?
For big numbers, yeah, but not like if it's small than that. That's how like merge sort works, right? Like merge sort, it's only like you should only do it for big.
Okay, so we have one opinion in the class. Anybody agree with that? Think that for small, like we use the 4-digit example. So for small numbers, it's going to be, you know, for 4 numbers, it's 16. But really, if you get to bigger numbers, it's going to be less multiplications than the normal. Who agrees with that? Okay, so you guys are in the minority if you agree with that. Everybody who disagrees, what do you think? Is it better or slower or the same? Okay, so we have one opinion that says it's basically the same. Who agrees with that opinion? Okay, so, all right, so we've got like 10% of the class with one opinion, 10% with another opinion. What about the rest of you? Yeah. Ah. All right, so we have another opinion, which says it kind of depends on whether the numbers are like maybe the same length or like different lengths as to which algorithm is faster. Who agrees with that? Okay, all right, so we kind of have a wide spectrum of of answers here. So really what we're going to answer in this class is how could we answer this? So actually somebody in the back suggested this, which is you could always just code it up. And then you could measure how long it takes for different values of n. So that's, you could do that. So actually, if you do that, if you try it with code, this is what it looks like, okay? So this red line, this is as n goes from 0 to 500. This red line is how much time in milliseconds my laptop took to multiply with the grade school multiplication, okay? And the blue line is how long it took with this new complicated algorithm. And this is going all the way up to digits that are of length 500. So who was right? Who's right? Who in the class is right? Who do you think? Is it better? Is it worse? Can we tell from this graph? Yeah, so we have one here, which again, he's saying like, hey, if you went bigger, if you just went bigger, trust me, the red line is gonna get bigger than the blue line. So our algorithm is gonna be better. But I will say like, it's actually, for these numbers, it doesn't look too good because like for sure, it's almost always worse, up to 500 digit numbers. So that's like, you're already not gonna do that by hand. You're writing the computer to do it, right? It's kind of hard to tell. There's also this question of like, hey, maybe when I wrote the code for this one, I'm just a really good programmer. So I wrote a really good version of that code in C. And then this guy, maybe it's a freshman who wrote it in Python and doesn't even know what they're doing. So they're doing a bunch of unnecessary stuff because the algorithm's complicated. So maybe they didn't get it. So that like, it's unclear, right? Maybe that's why it's slower, right? And then like, I think like you said, you pointed out, maybe if we run it for 100,000 digits or 10,000 digits, maybe it changes. So that's why like looking at algorithms with just code, it's actually hard to know which one's better than the other because there's a lot of open questions. There's also, I just want you guys to notice, there's something kind of funny going on with powers of 2 with the Karatsuba algorithm, all right? Where like, it seems to like slow down, and then for powers of 2 it gets much better, and then like slows down and it gets a little better for powers of 2. If you actually graph this out, it actually starts going back up. But we will argue, so if we can't do it by writing the code and comparing the algorithms, can we do it by proving it? So I don't know if anybody thought of this proof, but this is the proof I thought of, which I said I'm going to be a little clever, okay? I'm being taught this algorithm in class, right? So this is a new algorithm to me. The professor's not going to waste my time covering an algorithm that's not faster. Therefore, the algorithm must be faster. Who agrees with my proof that Karatsuba multiplication, that the algorithm I showed you is faster because I'm teaching it to you in class? All right, yeah, I guess you guys caught on, but this is actually not true. It's not faster. Or well, the proof is, that's not a valid proof. You can't use that as a proof. So maybe what we can try is, let's try to work out some examples. So we saw that 4-digit numbers take 16 operations. Does anybody want to take a guess? How many do 8-digit numbers take? Yeah. 64, that's a guess, 64. What about 16-digit numbers? Do we have any math with like, oh. It's 16 squared is what I'm guessing, but he's still trying to work it out. Okay, so we have a couple of folks in class guessing that even with this new algorithm, the number of steps is still going to be squared. Who agrees with that? Again, a minority of the class agrees, which is kind of weird because it's like you either agree or disagree. So everybody else disagrees. Is that what I'm? Or I guess there's 3 options. You agree, disagree, or I don't care enough. So is it who doesn't care enough? So they're not. Oh, that is not the third option. What is the third? What is that? What are you? Oh, I don't know. Okay, that's the third option. I don't know. Well, you have to guess. We're just guessing. There's no right or wrong here. We're in lecture. We're just guessing. So what do you guess? All right. Oh, we have somebody on chat. They said, I agree, LOL, Michael. So he is laughing out loud at home. Anyway, if you do think it through, you can actually work out for 8 digits. Yeah. Oh man, does that count? Should I count that as like bonus points for you? Okay, follow up with me after class. I can write down your name and I'll try to give you some bonus points. Yeah. 16 squared, this is 256. All right, so you guys know now, but we're gonna erase this. So what you can do is you can actually just work it out, right? Like you can write out the tree to see like what happens. So with 8 digits, the first thing I'm gonna do is I'm gonna split it in half. So I'm gonna have 4-digit multiplications. That's these trees. And then the thing to remember is like, I actually already did that work, right? Like we already talked through how we have 4 digits, I get 16 multiplications. And when I made these slides, I just copied this and then made it. That's how I got the bigger tree, right? So you can see here that it actually does take 64 1-digit multiplications, all right, for 8 digits. So what I'm going to claim is that this algorithm is at least n-squared operations. So it actually is, at best, the same as the grade school algorithm. And we're going to do this a proof by just counting. All right, so like more formally, more generally. So we are done with examples. We're going to consider the general case. My claim is that there are n-squared 1-digit multiplications in the leaves. And the reason I believe that is because when I worked out the 4-digit example and when I worked out the 8-digit example, for the 4-digit, I had 16 leaves in my tree. Each were 1-digit multiplies. And for the 8-digit example, I had 64 1-digit, right? So it's kind of squaring. So my guess is like, can I prove this for the general case? Like, does this always work? So the way we would do it is we kind of think about it in the tree structure again, right? So we start with one problem of size n. We split it up into 4 problems of size n divided by 2. ... You keep doing that until you get to the very bottom. And my question is, how many problems am I going to have of size 1? Like, I don't even care about the middle ones. I'm just saying, like, at the very bottom, how many am I going to have? And the claim is that I'm going to have n-squared. But we have to, like, prove that, right? Like, you guys probably know it, but I want to formally show you this is true, right? So one way to think about this is that for each level, right, each time I go down, I multiply the number of problems by 4, right? Because one problem becomes 4 problems. And then this one problem becomes 4. This one becomes 4. This one becomes 4. This one becomes 4. So each time I go down a level, the number of problems gets multiplied by 4, right? So on the tth level, so somewhere in the tree, somewhere in between, let's call it t, right? I will have 4 to the t problems, right? Because I'm doing like, here I have 4, here I have 4 times 4, here I have 4 times 4 times 4. You know, next level I have 4 times 4 ... times 4, and there's going to be t of them. So this is 4 raised to the power of t, right? Some like 8th grade, 9th grade, like basic multiplication, right? I will say this is where t equals 0. So we say this is t equals 0 because that's how we get, you know, 4 to the 0 equals 1. That's how we get 1 at the very beginning, all right? So on the last level, the problems are of size 1, right? So now we just need to know what is the last level. Because now I know how many problems are in each level. So how many levels are there, right? Because I want to ask how many problems are on the last level. So the way I get that is by figuring out how many levels are there. So for the levels, the number of levels, right? We start with size n. And when we go down 1 level, we divide by 2, right? When we go down the next level, we take that new n divided by 2 and divide by 2 again, right? So that's n divided by 4. The next level, we divide by 2 again. So that's n divided by 8. So on the last level, I'm going to have that n divided by 2 to the t equals 1. Does that make sense? Is anyone following along, falling asleep, maybe? Does anybody have any questions on these two pieces of argument? So one is that the number of problems at a certain level is 4 to the t. The second argument I'm making is that on the last level of the tree, or the number of levels in the tree must satisfy this relationship, where n divided by 2 to the t is 1. Because I know that on the last level, the size of the problems is 1. Cool. So actually, if we solve for t, you work it out, do a little bit of math. So you multiply by 2t on both sides. Then you take the log base 2. You get that the height of the tree is log base 2 of n. So who could have guessed that? If you guys remembered, you're like, you know, I don't know, merge sort or binary search. Do you guys remember how tall those trees are? Because you also split the problem in half each time, right? So in general, the height of a tree is like log base whatever, like how you're splitting it of n, right? Cool. But that's the index of this level, right? But my real question is, how many problems do I have on the last level? All right. So working out the math, if you guys have questions, you can look at this, but you can work out the math. The number of problems on the last level, we said was 4. The number of problems on any level is 4 to the t. On the last level, we know that t is log base 2 of n, right? So you can simplify this down. So 4 is actually 2 squared. When you have exponents, you can actually flip these. I don't know if you guys remember those rules, but you should be comfortable with rules of exponents, like work with math. If you don't remember and you need help, we're going to hold some like review sessions, like I'll give you like a list of rules for exponents, but you can flip them so that it becomes 2 log base 2 of n. And then this parenthesis is actually supposed to be here. So it's another correction, squared. And then 2 log base 2 of n, this 2 and the log base 2 essentially cancel out. Because you're saying like 2 raised to the power of what number would give me n. So exponentiation and logs cancel. So you actually get n squared. So there are exactly n squared problems on the last level of the tree. And that's pretty sad, because now we have just shown that this whole algorithm I taught you is pretty bad. All right. But wait, let's go back to our divide and conquer. So I'll tell you that the algorithm I taught you is not Karatsuba's algorithm. It's how you get to Karatsuba's algorithm. Because he saw these equations and he said, I don't think you need 4 multiplications. I think you can do better than 4. Because right now we have 1, 2, 3, 4. And because we have 4, it's n squared. And he said, no, I think you can do better. What do you guys think he did? This is where the cleverness comes in. You gotta like, you know, be creative. Gotta figure, yeah. I bet you he tried that. I bet you he did. And that is a good idea. It does not work out, but it is a good idea. And I bet you Karatsuba tried it. I bet you he spent a lot of time trying this, because the first time you discover something, it's not obvious, right? It seems like I'm going to tell you, and then you're going to be like, oh, that's obvious. But I bet you he spent a lot of hours thinking about this. Any other ideas, suggestions? All right, so I'll just tell you. So it feels like we need 4 multiplications. We need AC, BD, BC, AD. So this is just all the 4 combinations, right? But he actually figured out, he's like, wait, actually, I only need these 3. I need AC and BD. And then what I'm going to do is I'm going to add A and B. I'm going to add C and D. I'm going to multiply those. And with these 3 multiplications, I can actually get all 4 of these values. Can you guys maybe see how that's going to turn out? It's okay if you can't, because I'm teaching you this. So like you're not supposed to, but this is his thought process, right? So the values I need are AC, BD, BC, and AD. And he said for AC, he said, just do it. There's nothing clever there, just do it. For BD, he said, just do it. I can't help you there. Just do it. For these two, he said, wait a second. I don't actually need BC and AD. All I want is their sum. I don't want each one. At the end of the day, all I want is what is the sum of the two. So he said, well, it turns out that AD plus BC shows up right here. I circled the wrong ones. Shows up right here. So they're backwards. AD, BC. So he realized, hey, if I actually multiply these, that's equal to AC plus BD, which I already know, plus BC plus AD. Right? So with this, so he noticed that, and he said, oh, then I don't need to do these two separately. I just do this multiplication, which is going to be equal to this when you expand it out. And I'm going to subtract off AC and BD. Yeah. Yeah, that's perfect. Yeah, because we have the first two. So he's just going to subtract these off. And that's how I get the sum of BC plus AD. And he doesn't actually have to multiply both of them. So I will walk through this again, or not again, but well, I guess actually this is the key to the algorithm. So hopefully, or this is the cleverness where he like thought for a long time and said, hey, do I really need 4 multiplications? Answer is no, I actually only need 3. Does everybody see how this is? So this is just FOIL. And then what I'm saying is what you can do is all he wants is this. So you can subtract AC and BD from each side. This cancels out. And then this gets minus AC minus BD. So he's saying instead of multiplying this and then adding them, I can multiply this number and then subtract this and this. Right? So instead of doing 2 multiplications and adding, I can add, multiply, subtract. And in the big scheme of things, multiplication is what matters. Subtraction doesn't matter that much. So it's a little bit more complicated, but that's how you get. So this is the pseudocode. The only thing that he changed is he said, instead of multiplying them first, I'm going to multiply A plus B and C plus D. And then I'm going to subtract them off at the end. So there might be some bugs in here, but let's move on. That was the only difference he made. So now what is the running time? So the big change that happened is now we have 3 multiplications instead of 4. So all the same arguments still apply, right? So at each level, instead of 4 to the t, now we have 3 to the t. We still have the same number of levels because we're still dividing by 2 each time, right? So that didn't change. And then if you work out the math, you get to n to the log base 2 of 3, which is around 1.6. So with that one little tweak in his algorithm, he now has an algorithm that is not n squared, but n raised to the 1.6. And this is much better. So it's not linear, but it's much better. As n gets bigger, n squared just explodes. N to the 1.6 also explodes, but much less quickly. All right. And now I hinted at this last time, which is, can we do even better? And the answer is yes. And somebody actually proved that the optimal you can do is n log n. And log n is really, really slow growing. So this is almost linear, but not quite. And they actually prove this is the fastest you can do. You're not responsible for this. This is just a historical context. So you can get excited because Karatsuba discovered this in like the 1950s, I think, or maybe earlier. 1963, this guy named I think Tom Cook, might be Tom Cook, but I think it was Tom Cook. He figured out that you can, instead of breaking it up into 3 n divided by 2 problems, you can actually break it up into 5 n divided by 3 problems. So he did a lot more like arithmetic and little cleverness, but it's the exact same algorithm, except he's like, oh, instead of 4 multiplications and Karatsuba needing 3 multiplications, I can actually get you to need 5 multiplications, but each one decreases the size of the problem into 3 pieces. So it turns out that that's a little bit faster than Karatsuba. So it's around n to the 1.46. And then these are just more complicated. This one is the coolest one, Führer in 2007, so not too long ago. He discovered you could run an n log n times 2 to the log star n. For all intents and purposes, if you plug in n to the number of atoms in the universe, which is like whatever quadrillions of atoms, this ends up being n log n times like 4 or something like that. So it's like he was really good. But then these guys came along in 2019, not 2 years ago, and they proved the fastest algorithm possible for integer multiplication at n log n. And if you look up the paper, it's like super complicated. I don't even understand it, but there are still problems like that currently in computer science where people don't know whether we have found the fastest algorithm, and where we need people like you guys to look at the problems and say like, I don't know, there's a little bit of cleverness I could use here, right? Cool. So hopefully at this point, you are familiar with Karatsuba integer multiplication, and you learned a little bit about divide and conquer. Again, like we said, for the big questions, I think this practice, I might end up making it part of the homework because we have only 3 minutes left. We were going to do a little bit of practice with pseudocode, so like how to go from pseudocode. It's in the slides. It's also in the lecture notes. I will probably include it as part of the homework for you guys to get familiar with it. But we were going to essentially, like I did notice a lot of folks in the class were a little bit hesitant about C++. During lecture, a lot of the algorithms we cover are more mathy, because it's more about the problem you're solving and the technique you're using and arguing how many steps it's going to take, right? Than it is about writing it in code. But at the end of the day, you need to write it in code. So what we were going to do in lecture was practice a couple of things where, you know, I give you the pseudocode and then you guys tell me like, okay, this is what it would look like in C++, right? I'll give this for homework for you guys. It's not hard. It's not hard. So we'll skip that for lecture. We'll leave it for later. But I did want to ask before we leave, how was the pace today? Question, is it like I want a thumbs up if you think it was too fast. Cool. So actually I can go faster. Okay. So, wait, thumbs up if it was too fast, if the lecture was too fast. Okay, thumbs up if it was too slow. Oh, okay. Oh, wow. Okay. All right. So we'll keep the pace. But yeah, that's it for today's lecture. Thank you guys for coming. Hopefully, oh, he said, Jewel says, don't go faster. All right.